all of you should be able to hear me. Can someone confirm? And in either room, I guess in both rooms, that we have audio? Yes, okay, that's great. Please send me a message if we lose sound during this session, because we did have some issues like that last time. And hopefully we will not have similar technical issues. Okay, so I'm going to enable my camera now so you can see me a little bit, but then I will switch to sharing my desktop so you can see what we're talking about. And what we're going to do for the roughly next hour, we are going to go over the questions that you submitted on Senatus. Okay, so we are going to answer them in order of decreasing popularity. But also what I'm going to do at about 3 p.m., a little bit after 3 p.m., is I'm going to go over a few of the questions from the midterm and discuss the solution a little bit. I will not go over all of the questions that we had in the midterm. I'm focusing mostly on some questions that some students had some challenges, etc., based on the grades that you received. So then once we have done that, I will finally enable those regrades for the midterm. I wanted to do this a little bit of discussion first before we enable those regrades. Okay, so this is how this session is going to go. So without further ado, I will enable screen sharing so you can see some of the material I will pull up on my screen. I'll do this for both rooms. Okay. All right, and all of you should be able to now see the content of my screen, okay? And I have opened up here the Senatus link, and I'm going to start basically answering all of these questions in order of decreasing popularity. Let me refresh here. And all right, so the most popular one was a question from an old final that said, that basically asks you to count the number of parameters that we learn for a number of different methods. Okay, and the particular question lists about 5 or 6 sub questions from that final, and let's go over them. So the context here, for those who haven't seen the question, is that we have 800 examples in the data set, and each example is a 10-dimensional vector. Okay, so starting from sub question number 9, from that question, we're asked to provide the number of parameters that we're learning when we're doing density estimation for basically 10-dimensional vectors. What we have here is a little bit messed up in terms of annotation. Basically, the question on that final was x belongs to r to the 10. Okay, so how many parameters do we have in a single isotropic Gaussian? We have one Gaussian distribution. The fact that it is isotropic means first that we have one scalar as our variance. That's it. Our whole covariance matrix is represented by one scalar sigma. So if you remember that covariance matrix is sigma squared times identity. And then of course we also have the mean for the Gaussian. So the mean has to be a 10-dimensional vector. So all in all, we have 10 for the mean, we have one parameter for the variance, and the total is 11 parameters. Okay. Number 10 here says it's a density estimation problem again, only this time we do not use an isotropic Gaussian, but we use a diagonal a Gaussian with a diagonal covariance. So what this means is that the off-diagonal elements of the covariance matrix are 0, and we only have one element, we only have the diagonal elements, each of which corresponds to the variance of each variable that I have. I have 10 variables, so I have 10 elements in the diagonal of the covariance matrix. So in this case, I will have 10 parameters for the covariance matrix. I will have 10 parameters for the mean of the distribution, and the total will be 20. At 11, we have again a density estimation problem. Only this time we have the full covariance matrix. Like before, we will use 10 parameters for the mean, but now we have a full covariance. What does the covariance matrix look like? It's a square matrix where it's the number of variables times number of variables. So it's going to be 10 times 10. It's going to be 100 parameters, okay? We have to be a little bit more careful. So if I just count them like that, I have 100 numbers in the covariance matrix, and I will have 10 numbers for the mean. But the covariance matrix is a symmetric matrix, okay? In particular, the upper triangular part is the same as the lower triangular part, just transposed, right? So in that case, we have to be careful. We should count the diagonal. We should count either the upper triangular or the lower triangular part, but we should not count those variables that are the same twice. Okay. And there's counting is easy. The base classifier using diagonal Gaussians. So that was 12, and the way I would count this is I would count 3 parameters for the priors. Okay, we have in this particular example, because let's look at the question here, just to be clear, because the question on Senatus doesn't give all of the details. We are looking into 12, and here it mentions that we have 3 classes, right? So we are training a base classifier for a 3-class classification problem, right? Which means that we are going to have 3 Gaussians, and we're using 3 diagonal Gaussians. What this means is that I will need the parameters of the prior distribution. In this case, I would accept as correct answers that say I'm spending 3 parameters for this prior. But if you also tell me it only suffices to store 2 parameters because the third one is uniquely determined by the fact that the 3 priors need to sum to 1, I will also accept that. And then for each one of those class conditionals, we have a diagonal Gaussian, and we've already counted that before. It was 10 plus 10. 10 for the mean vector and 10 for the diagonal covariance matrix, a total of 20. So 3 times 20 equals 60. So the 2 answers that I would take as correct in this, I would accept as correct in this question would be 62 or 63. Okay, and then 13, density estimation, right? So this is the Parsen density estimator. Okay, we're using a kernel, a Gaussian kernel, an isotropic Gaussian kernel, whose variance, whose width, essentially that width of a neighborhood, has been fixed in advance, and it's a hyperparameter. So we don't count that as a parameter that we have to learn. And it's trained on a dataset containing 800 examples. So in this case, for methods like that, we basically, the basic simple answer is that we store the whole data set. So in this case, we would store 800 points times 10 at the dimension of each point. We're storing 8,000, our model consists of 8,000 scalars, because every time I get a new test point, I have to go back, I have a different neighborhood, and I have to go back and evaluate using all of my data sets. So the answer here would be 8,000. And 14, it's a multi-class classification problem for 3 classes. And it says the method here is, again, the Parsen window classifier with an isotropic Gaussian kernel whose variance has been fixed in advance. It's the same answer. In this case, the kernel looks a bit different, as in we're doing, instead of doing this soft voting that we use for density estimation, we have this hard voting, okay, where we, in the end, we'll use a sign to select positive or negative for the label. I'm sorry, this is multi-class, but this does not change anything. In this case, again, we will have to store the whole data set. Okay, this is the number of, as what we would consider the number of parameters here. So 800 times 10, 8,000. And the last one here was 20, a density estimation problem using a mixture of 3 diagonal Gaussians. Right, so this is the same as one of the questions that we saw before. Yes, it's the same as 12, right? Okay, so in this case, again, you would need either 2 or 3 scalars to represent the prior, to represent the weight of each Gaussian in the mixture. And then for each one of the Gaussians, you would need a 10-dimensional vector for the mean, and you would need the diagonal covariance matrix, which also requires 10 parameters. So it's going to be 3. We also do, so in this case, 3 times 10 plus 10, which means 60. And then 2 or 3 parameters, both answers are fine for the prior. So 62 or 63. And so there was someone was asking a clarifying question. Let's go back to the messages. Oh, that's a good point. So some in both rooms, I think, some people are saying, well, we will need to also store the labels. Okay, so I think you guys are right. You guys are right here. For each one of the 800, in the case where we're doing classification, right? And so we had 2 different questions. One was for density estimation using the Parsen, like a kernel using the Parsen method. And the answer there is 8,000. But when we go to the multi-class classification problem in 14, I think that the few people who commented that we need to add the labels, to count the labels, are correct. So yes, in this case, it would be 8,800. Okay, thank you for that. Okay. So right, that concludes the first question in the Senatus. All right, any? Okay. Sounds good. Okay. Next question. What parameters does the k-means algorithm learn? Also specify their dimension. Okay, Sabi, I see that Sabi is still wondering about the previous question. Yes, for each example, you would store the ID, the class ID, Sabi. Okay, so we will count the class ID, which is some kind of integer, right? 0, 1, 2, or something like that. Okay, next question. What parameters does the k-means algorithm learn? Specify their dimension, okay? So the k-means algorithm, if we go to the, let me rearrange these windows a bit. If we go to, oh, this is where I wanted to go, okay. This window. Okay, so what I wanted to show you, okay, is this slide basically. This is the k-means algorithm, and here this optimization basically decides the value of the parameters of the algorithm. What are the parameters of the algorithm? Here basically we have, for each cluster, for each one of the k clusters, we have for each one of the k clusters we have a mean. Okay, it's the mean of the cluster, the mean vector of the cluster, and then we have these sets. Okay, for each cluster we have a set that contains basically we have a set of sets that forms a partition over all of our examples. Let's say the first set is the first cluster, the second set is the second cluster, etc. So one simple way to represent that is to say that for each point xi, I will store something like a class label. In this case, it's the cluster number. It's like a cluster label. Okay, so eventually the number of parameters we end up learning and storing is k times the dimension of the space, because we have those k means. Okay, so for each mean we have number of dimensions times k, so this is k times the number of dimensions. And in order to store the information of which point belongs to which cluster, one simple way to do this is to say I will store one integer, one label for each example. So we can count them as one scalar also, and just say it's the number of points, the number of examples in my training set. Okay. Okay. Third most popular question, yes. Gaussian naive Bayes will always give a linear decision boundary. This is a very good question. I will hold off, and I will get back to this question after we have seen the solution to one of the midterm questions. Okay, we will get back to this because it will help us make sense of it. All right, the fourth question. If you train a linear regression estimator with only half the data, its bias is smaller compared to its bias if it were trained with the full data. Okay, true or false? The answer is false. The way bias is defined, it is not affected by the size of the data set. So in particular, the bias is a property of the model that we use. It does not really depend at all on the data set, on the data set size in particular also. So if you remember in the discussion that we had in class, we were basically explaining this bias as a kind of approximation error. In particular, we say that maybe the true phenomenon that we're trying to capture is non-linear, but we are using a linear model, for example. Okay. In that case, our linear model is incapable of fully capturing the underlying phenomenon because the underlying phenomenon is non-linear. So we have an inherent approximation error. There exists no linear model that can do a good job in this problem that I'm giving to you as an example. And that has nothing to do with how much data we have collected, okay? So the answer here is false, okay? On the other hand, if we're talking about variance, there is a very, very, very direct and simple connection between the size of the data set and the variance. The variance essentially goes down as 1 over the number of points in our training set. Okay, the order of 1 over the number of training points. Okay, so this is that. Let's move on. We can get multiple local optimum solutions if we solve a linear regression problem by minimizing the sum of squared errors using gradient descent. The answer is generally yes. We can get, if we're being a little bit careful and maybe a little bit pedantic here, there can be multiple global solutions. Okay, this will form a convex problem. Okay, this gives us a convex problem, but it can have multiple different solutions, all of which are globally optimal. Okay, being a little bit pedantic here, any globally optimal solution is also locally optimal. Okay, so the answer is yes. We can get multiple local optimum solutions for this problem. Okay, we just have to be a little bit careful about the description and the language that we use. So there's a question here that says, the next question, it says, I guess decision tree boosting won't be a focus in the final. First of all, I would like to stop here and say, no, nobody told you that. Okay? There's no reason for you to think that decision trees and boosting questions will not be part of the final. Okay? Whatever was covered in class, you should be familiar with it. And that includes the general discussion here on ensemble methods. And make sure you can, okay. Yes, so that includes the general discussion here on ensemble methods. And this whole discussion about bagging and the introduction to boosting. But it also includes material that you have seen here, in particular on the method AdaBoost. Okay. So there was a whole section, a whole discussion on how AdaBoost works, and there's also the analysis on why if you combine weak classifiers using AdaBoost, you get an exponentially decreasing training error. Okay, so if I were to give you a natural stopping point, is slide number 22 in this slide deck by Arti Singh and Carlos Gestrin. So once we go to boosting results and generalization error bounds, we don't care about the rest of this material. But up to 22, you should be familiar with the material. Okay. Okay. All right. Next question. It says, choosing different norms does not affect the decision boundary of one nearest neighbor. True or false? Does not affect. I think this should be false. You think about it. This should be false. Yes, it is false. It changes the topology. Like you should try to convince yourself by considering two different balls, two different types of balls. So you will go in and you will compute and you will see how things work out. You can draw those Voronoi decision regions for the standard Euclidean norm, and then you can go and consider something like the L infinity norm or L1, and you will see that those decision boundaries will change. Okay. All right, another interesting question on, I like this sequence of two questions here. What increases the risk of overfitting and what increases the risk of underfitting? I like the sequence of these two questions here because there's a subtle difference between the two. So the first one says, circle what increases the risk of overfitting, okay? And it says having a larger number of training examples, having a smaller number of training examples, increasing the capacity of the training algorithm, or choosing one with larger capacity, or D, decreasing the capacity of the training algorithm, or choosing one with a smaller capacity. So, okay, so we're talking about overfitting, which means basically a high variance. We have high variance. The discussion we had before might help us a bit. And it says, and the answer here is basically having a small number of training examples can increase the risk of overfitting. It is true. And increasing the capacity of the training algorithm can also increase the risk of overfitting. So we would circle here B and C. Okay. A will actually reduce the risk of overfitting. One of the things we have mentioned is a large data set. A large training set is considered to be a very good regularizer. So A has the opposite effect. So we will not circle it. And we will also not circle D because decreasing the capacity of the training algorithm based on all the discussions we've had is basically will reduce our risk of overfitting. Okay. In some sense, we tend to get a lower variance predictions. Now the jump to the next question is interesting because in this question we saw that we can overfit either by having a small number of training examples or by having a high capacity model. Now, if we change the question to the risk of underfitting, we have an important difference here. We have an important distinction. Underfitting fundamentally has to do with bias. So when we talk about underfitting, we mean that we have a model that is too simplistic, that is not powerful enough to capture, let's say, the peculiarities or the nuances of the true underlying phenomenon that we're trying to capture. Okay, so as we discussed before, 10 minutes ago, the number of training examples has nothing to do with bias, okay? So the number of training examples has nothing to do with underfitting. So if we increase or if we decrease the number of training examples, it will have no bearing. So we will not circle A, we will not circle B, okay? However, we need to circle one of C or D. As we discussed, this bias depends on the capacity of the model. So if we have a model of insufficient capacity, that's when we get high bias, and that's when we underfit, okay? So decreasing the capacity of the training algorithm is what will get us to underfit, is what will increase our risk of underfitting, okay? So this is the correct answer here, D. Okay, and then how is the number of kernels chosen? So the next question is about convolutional neural networks, okay? and it says, how do we choose the number of kernels? And in a particular slide in the lecture of CNNs that we had, we see that 64 kernels are chosen as the magic number. How do we choose that? And the answer is the typical unsatisfying answer that I give you, is either through trial and error or through following best practices that we see in literature, etc. So this is another hyperparameter. How do I choose 64, right? It depends on the problem. Some problems will perform best if I were to choose 64. In some problems, it's best if I choose 8, etc. So this is another hyperparameter. And the only universal tool we have to help us make a decision here that works across problems and across situations is using a validation set to tune our hyperparameters. This is the one, hammer that we have to address questions like that. Beyond that, in very, 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 very particular problems, in very specific situations, you might have some side information. You might have some domain expertise that helps you choose some hyperparameter values over others, but that is a bit rare. In general, we use our validation set. We carefully follow the standard methodology, and we come up with an approximate good number of kernels. Okay, this is the generic answer. Is the slides probabilistic graphical models included in the final exam? No, we did not cover that in class, so you will not be asked about PGMs. Okay, so it's a very interesting topic to be familiar with. I encourage you to skim over it so you know what kind of terminology people use, what kind of tools are available, but you will not be tested on it this Thursday on our final exam. Another question here says, these did not understand SVMs. A quick explanation should be helpful. It should, but it's also not possible. It's unfortunately, we cannot repeat a whole lecture on SVMs here. It's not an easy topic to explain in 2 minutes either. The main idea, obviously, as I bet you already understand, is that it's a class of methods that maximizes the margin between the decision surface and the given training set examples. But the details are many, and it gets complicated. We have multiple formulations. We have hard SVMs, we have soft SVMs. Unfortunately, I cannot repeat this whole discussion here. Okay? So going to the next question, could you give a brief explanation of the Bayes and naive Bayes classifiers and how to visually imagine them? Okay. Okay, I'm not sure if visually I'm not sure I have a good answer to this. I can give you a brief explanation of the difference between the two. Okay, so we have the Bayes classifier, okay, which is, just to be clear, the Bayes classifier is a family of methods, and we get a specific method once we commit to a specific way of estimating those class conditionals. So there's a density estimation step that is inherent to the Bayes classifier, and it is right. And we have a modeling choice to make. How do we estimate the density of the different classes, right? How do we estimate the density of the class conditionals, as we say? And once we make that decision, we get a method. So we could use some kind of we could use the Parson window method to do density estimation. We could use histograms to do density estimation. We could use we could model our class conditionals as Gaussians. We can use those parametric models to do density estimation. The main difference, and eventually, just to finish that discussion on Bayes, eventually, once we have a reasonable estimate, density estimate for all of those class conditionals, we use the Bayes rule to get the probability, the posterior probability, as we say, the probability that a new point belongs to class 1 or versus class 2. Okay. Now, the difference between Bayes and naive Bayes has to do with the modeling choices that we make. Naive Bayes is again a family of methods that is restricted in a very, very particular way. We make the extra assumption that conditioning on the class, okay, if we condition on having a point that comes from class 1 or from class 2, etc., each one of the variables are independent. Like the examples that come from that class, I condition on class 1, then the distribution that I see is such that the features are independent. Okay, so at this point, I have a much simpler method because for example, if I were to do a modeling assumption that is a Gaussian, this naive Bayes extra assumption tells me that I have a diagonal covariance matrix. That's what it means in this case, right? And following on the discussion we had earlier on counting the number of parameters for Gaussians with a full covariance matrix versus Gaussians with a diagonal covariance matrix, you can see that the naive Bayes classifier has a much smaller number of parameters. Okay, now one way to visually start comparing the two is by understanding that this naive Bayes assumption kind of throws away covariances. Okay, so let me see. There's a little bit of feedback. Let me do this. Okay. So this naive Bayes assumption disregards any covariances between and any dependence actually between the different features conditioning on a class label. So if you were to visualize the shape of those class conditionals in space, the fact that you have a diagonal covariance, for example, it gives a shape. It's described by an ellipse, that is aligned with the axis. It's not rotated diagonally in some sense. Okay, that's one visual way to think about it. But otherwise, I do not know of a good visual explanation of these two methods. Okay. Or you could refer to some of the plots where we see all of the class conditionals in feature space. Okay, we see those densities in feature space like little hats, little colorful hats. And then depending on the priors, those become smaller or bigger, and then they have their own shapes. And where they meet is where those density surfaces meet is where we have our decision surface. That's another visual image you can have in your head on the Bayes classifier. Okay, can you briefly summarize why and how backpropagation is one of the 7 wonders of the world? This is a loaded question, and I will not address it. I will instead go do what I told you I'm going to do, is go over some of the questions of the midterm. Okay, and all right. I do not have all of them. So here I have borrowed some of the questions, some of the responses from your classmates that did well, and I have just left some of the questions available, so we can go over some of the questions that there were some issues for a few students, etc. Okay, so I will try to keep this clear, to keep this quick. Histogram methods can easily be used with high-dimensional inputs. That's false. That's the basic introduction that we had to the curse of dimensionality. K nearest neighbors trained with large values of K. Let me make it bigger. K nearest neighbors trained with large values of K is more likely to overfit than with smaller ones. The answer is false. We have high capacity for a small number of neighbors. Okay. Suppose you train 2 models on a data set, a polynomial regression of order 2 and a feed-forward neural network with 4 hidden layers. After training, the validation error of both models is roughly equal. If your goal is to achieve a low test error, you should choose to use the neural network. The answer is false. No, since we have had a validation error that is the same for the 2, we should go for the simpler model, okay? We generally understand that simpler models generalize better. In particular, the gap that we might have between validation and test, we expect it to be smaller for simpler models than for more complicated models. So when you see equal performance, always go for the simpler model, okay? Okay, for any classifier, the empirical risk evaluated on the training set will converge to 0 when the data set grows to infinity. The answer is false. And the reason is this approximation error that we have, the bias. So if my classifier is not strong enough, does not have enough capacity to capture complex phenomena, the number of points doesn't matter. The number of data set, the size of the data set doesn't matter. A linear model will always be insufficient if my true phenomenon is quadratic, let's say. Okay, so the answer is false. Let x1, x2 be 2 data points and let k be a kernel function. And the question is, this difference between the reverse k of x comma 1 minus k of x comma 1 x comma 2 minus k of x2 x1 can be greater than 1. The answer is false. The kernels that we use are symmetric. So the answer here is always 0. And finally, actually, I will not discuss this. This was like a difficult true-false question. If you do the math here and considering that essentially the kernel describes, in some sense, the inner product between phi x1 and phi x2, you can bring it back to trigonometry, and after some non-trivial calculations, get that this is true. This is not a very important question for you to know for the final. It was just one of those questions that we use to identify students that are particularly strong in math. Okay. All right. So this was a relatively simple question, and hopefully it's a good question, I think, and you should try to practice it, even though you will not get the same question in the final, obviously. But it's a very simple thing. We have a regression problem, and we're asked to compute all sorts of things. First of all, what is the prediction, all right? And what is the error of the prediction we're making for a particular given model, this Vita 1, okay? So we start by giving all of the predictions that this new model gives, and we have the true labels given to us in Y, so we get this difference between the two, and then we have to square all of them and divide by the number of points in order to get the mean square error, right? or this squared loss, as we say. The next question asks you to basically write the loss with respect to only one of the data points, x1, okay? And here, basically, we had the same thing, like given x1 and y1, the label corresponding to x1, we subtract here the prediction that is given by a model described by parameters β1, β2, and β3. And then we have to square the whole thing. And in the end, this expression simplifies nicely in this form. So now we have a yes, we are. Alexander is asking. Alexander is asking, I can't see your screen. That's interesting. So which room are other people having a challenge seeing my screen? Room 1 is good, says Tong. Alex says room 1. Emmanuel says that in room 2 things are fine. So Alex, you might need to find my window and pin it. There's a little icon that it's the icon of a punaise, and you click on it, so it always shows you my screen, and that should fix it because everyone else can see. Oh, that's a good point. Fernanda made a good point. You might see 2 or 3 windows with my name on them. Like one will be a video of me, okay, but another one shows my desktop. Okay, I'm sharing my screen with you, so you should try to find that window and put a pin on it so it always shows you that. Okay, all right, Alex found it. All right, good. So yes, as I mentioned in the beginning, we'll spend a little bit of time going over some of the midterm questions to clarify some questions. So then I can open the regrades after having this discussion. Okay. Okay. So the solution here is simple. Now that we have this loss function that only depends on the first example, we can compute a gradient. Okay, this is also a very simple problem of linear algebra. You should be able to compute simple derivatives like that. Okay, and then if we plug in the particular model, this β1 we were talking about, we can get the particular value of the gradient with respect to the example x1, y1, right? And finally, using this gradient, we can perform gradient descent. So you start with your original model, negative sign, step size, the gradient you computed, and then it gives you some result here. And the question is, how has the loss changed? So you can compute the loss at the previous model, the loss at the new model, and just say that the loss has increased or decreased. And just a quick answer on this last bit. This last sub question, does there exist a linear model with 0 training error on the given data set? The answer was yes, and this is one example of a model that gives a linear model that gives 0 training error. Okay, and the weights are given by this vector basically. And more generally, there are a couple of equivalent linear algebraic conditions for establishing whether it is possible to achieve 0 training error. Okay, and one way to describe this is to say that vector y, the vector of labels, is in the span, as we say, in the linear span of the columns of x. Okay, so if we go back, if y is in the span of the columns of x, as in there exists scalars such that I will multiply the first column by the first scalar, the second column by the second scalar, and the third column by the third scalar, and I will get this vector. that means that that's what we say y is in the span of the columns of x. In that case, yes, you can have a linear model that gives you 0 error. An alternative is to say that getting this kind of solution here, that x transpose x is invertible, okay? So next question, I guess I will spend a little bit of time here and then we'll wrap up. This is the naive Bayes question, right? There were a few people who were confused here. For the first point, the first sub-question, we were looking for the full Bayes classifier. This means that we do not make the naive Bayes assumption, okay? When we make the naive Bayes assumption, those words here would be independent. We would be replacing this sequence of words conditioned on the class. We would be replacing it with the product of individual words, probabilities of individual words conditioned on the class. For full Bayes, this is the model. It does not get simpler than this. And now using this model, it's a very standard way to train the full Bayes classifier. We just count the occurrences of each class, okay, in order to find the priors. It's just counting. And then we do some kind of estimate for the class conditionals, some kind of density estimate for the class conditionals. And in this case, we count, if we do not make any further modeling assumptions, okay, and we expected you to not do any further modeling assumptions, you just count the occurrences of specific sequences. How many times have I seen W1 followed by W2, followed by W3, etc.? And we count them here, okay? And then we use the Bayes rule essentially to make our predictions. So what is the problem with the full Bayes classifier? What was the issue, and why do we often resort to the naive Bayes classifier? It's that even in a large corpus of text in this particular application, most of the sequences of words will be empty. We will not have examples where W1 is followed by W2 is followed by W3. In some sense, we're getting bit by the curse of dimensionality, okay? So we will not be able to estimate these fractions very well because most of these will be exactly 0 in our data set, okay? So then when we go to naive Bayes, we have this conditional independence. This is the assumption here. The probability of this sequence conditioned on the class ID can be broken down into a product of words conditioned on this class ID, okay? This is a naive Bayes assumption. And now we have much simpler probabilities to estimate. They're much lower dimensional. And finally, to train this naive Bayes classifier, we count how many occurrences of class 1 we had, how many occurrences of class 2, and then for each one of the two classes, we count basically the frequency of each one of these words, okay? And in the end, we get some result. We use the Bayes rule again, and we get some kind of prediction. The interesting thing that happens once we add this Laplacian smoothing is that the prediction can change, okay? One of the interesting things we were going for is that in the end, the probability of tennis will be higher than the probability of Olympics in this particular example. But the main new technical thing with Laplacian smoothing is this add one smoothing. As in, whenever we count occurrences of words, specific words in a specific class, we always add one. And we make up for that in the denominator by adding the requisite number of ones again. So that the whole thing ends up being a probability mass function again. Okay. So in the end, when we do this kind of normalization, the things change, okay? And we have different class conditionals. So now that our class conditionals are different, we have to recalculate our posterior, and which in some cases, and in this case in particular, it can change our decision, okay, for classification. All right, and actually this is the final one, and this is where we're going to end. The last one was a base classifier with Gaussian class conditionals with different covariance matrices. We have had an older question that said when the covariance matrices are the same, we get a linear decision boundary. Well, in this case, when the covariance matrices are not the same, this decision boundary is not linear anymore, and it's described by a quadratic of this form, okay? And your job in this question was to find the parameters of this quadratic, this matrix A, this vector B, and this scalar C, under these assumptions on general Gaussians. And the way to do this is to start with a decision boundary. We have a decision boundary that is given by this. This is actually the rule that is given to us by the Bayesian classifier. Whenever these two probabilities are the same, we are on the decision boundary, right here. Okay, so then we start substituting. We have variables for the priors. We have specific representation because of our modeling assumption for the class conditionals, and we can replace them all in there. We can move some terms around. We bring, in this particular case, this student brought all of the constants here. And then the typical thing that we do when we have those exponentials in this form, we take a logarithm, which will simplify the expression quite a bit and turn some multiplications into additions, which makes our life easier, okay? So after some manipulation of terms, we end up with a few quadratic terms, like this is a quadratic term. This is a quadratic term. Why? Because it has x before the matrix and x after the matrix. This is a linear term because it only has one x. This is another linear term. It has the x after the matrix, right? One thing that we saw is that some students were not very comfortable with matrix vector multiplication, and it's very important to brush up on these things because, for example, some important properties like commutativity do not apply here, okay? And they can make a big difference. And yes, finally, if you bring it all into this form, if you collect all of the terms, the similar terms, all of the quadratic terms in here, all of the linear terms in here, and all of the scalar terms in here, you get some kind of scalar that looks like this. You get some kind of vector that looks like this, and some kind of matrix that looks like this. So the correct answer has this form. This is not the only correct answer. If we change some signs, if we flip a couple of signs, we will again get a good answer, but this is one correct answer, okay? So now it is time for me to go back to the question that I skipped earlier, and this is how we will end this session. There was a question that said, one second. Okay, this is the question. Gaussian naive Bayes will always give a linear decision boundary. Okay, so we have a Bayes classifier that uses Gaussian class conditionals, okay? But we're making this naive assumption, which means what? Which means that all of our covariance matrices will be diagonal. So it restricts us to diagonal covariance matrices. So the assertion here is that we will always get a linear decision boundary. Okay, let's go back to the solution here and see what that means. Let's assume that we have general diagonal covariance matrices for our class conditionals. Okay, this means that this sigma 1 here and this sigma 2 matrix here will both be diagonal, but they will be different matrices. This means that this matrix A in the end will be diagonal, but it will be a non-zero matrix, a diagonal non-zero matrix. If we go back into this expression, we will see that it is a quadratic expression because this A is non-zero. So generally, we do not have a linear decision boundary. So the answer is false. Okay, and this is about the end of our hour. I invite you to submit more questions to the class forum. I think that yesterday I responded to some questions that were asked in the past few days, and I will make sure to respond to them tomorrow and the day after, so that you have all of the answers that you need by the final. And with this, I will leave you because I need to also leave for the airport. I hope you get some good preparation, and good luck on your final on Thursday.